Assalamu alaikum ji. This is the third lecture of the course Numerical Methods, which is MATH 351, and just a revisit of the previous lectures. In the first lecture, we just gone through the contents of the course, and in the second lecture, uh, we started with the mathematical preliminaries that we require to continue applying the approximate methods that we require in this course. Okay, so to implement those techniques, we require some concept from the calculus. So we have an idea in the last lecture about how to do the rounding or chopping of the real numbers, and with that connected the idea of the absolute error, relative error, and the percentage errors. And then we move towards the Taylor series, and in the Taylor series we have seen that how we can represent a function into the polynomial form, and then uh, how can we also quantify the error associated in any of the approximations. And we have seen the concept of the truncation. We just revisit the concept of the truncation error. And today we will continue revisiting one of another content and connecting that with our first topic, which is solution of the one variable equation. Okay, we'll start that topic today. Just a starting point of the first method, because that is connected with the intermediate value theorem actually that we learned in the calculus. We just revisit what is the intermediate value theorem, and then we try to go ahead with the first topic about the solution of the one variable equation. Okay, so I'll just give you the graphical representation of what the theorem is. We just wanted to revisit that. Okay, so let's say consider a function. So consider a continuous function on interval. So this is the notation that we can use to represent a continuous function on some interval. For example, um, uh, log x is continuous on 2 to 5. Okay, so I can so this is a function continuous on this interval. Okay, and m is a real number between f of a and f of b. So for example, I just plot, so this is a and this is b. Okay, and for example, this is the function f. Okay, so this height is f of a height, and this height is f of b. So this theorem says let m be so this is a hypothesis. Let m be any number between the height f of a and f of b. So for example, m is a number at this height. Maybe, for example, m is a number over here. If this is a height, so it says corresponding to this height, there is a value x such that f of x is same as m. Okay, you can also see that this obviously this is the function value at x. This point, this height is actually the function value at x. If you take any number, any height between f of a and f of b, that might be here or might be there, there will be a point over there, and that point actually correspond to some x value. Okay, so the image of that x value or the function value of that x value is same as that height. Okay, so this is the intermediate value theorem. Now we'll see how it helps us in solving equations. Okay, so for that I will be using consequences of the intermediate value theorem. That is called a corollary. Okay, that is a deduction from the main theorem. So I will try to go towards that deduction by using again a graphical view. Okay, so let's say there is a function which is continuous on interval a and b. Okay, and one of the height is positive and another height is negative. Okay, we can have obviously any heights. Okay, we just consider for the sake of discussion one of the height is positive and other is negative. So let's say at point A we have a positive height. So let's say this is the value. This is a f of a. Okay, so this is f of, and let at point B this is the value of the function. So this point is b f of b. So the height is over here f of b. Now since it is a continuous function, so these 2 points will be connected through a curve which does not have any discontinuity. It does not have any jumps. Okay, so it does not have any gaps. So these 2 points will be connected through any curve, okay, which is not discontinuous. So if I just draw any curve that is continuous, so let's say I draw a curve like this. Okay, connecting 2 points. Now if you see one of a height from where this curve is passing is this height. What is this height? What is the f value? It is 0. The f value is what? It is 0. Okay, and so it means if I try to see from the intermediate value theorem, 0 is a height between f of a and f of b, and corresponding to this height there must be x value for which, so height is 0, so I'll say, so m, so if you try to connect with this, the value of m is what? 0. Height is 0. Okay, so there is a some point p for which this is equals to m, or in other words it is equals to 0. And where this point p is, this point p is between a and b. It must lies between a and b. Okay, so that x which is over here is between a and b, between a and b. Okay, it's somewhere between a and b. So it means this is the point p which lies between this interval, such that at this point function is what? 0. Now if f of x is my any equation, and if I know that such a scenario is occurring, that I should know that there is a point at which the where the function will become 0. Okay, so for example, let me just take a bit of a space here. So what are the conditions we impose? First let's collect those information together and just try to then summarize it. Okay, so our first condition is these are called hypotheses. Okay, so for some conditions you conclude something. Okay, so the first thing we say, f is a continuous function on interval ab. This is the first condition. The second condition we impose that one of the height is positive, other is negative. Okay, it can also be seen as that the function at point a is negative and the function at point b is positive. It can also be seen like this. Okay, but for the case one, maybe for the first scenario, just to try to understand this, we are saying that the signs of f, or the value of f at a and b, have different signs. They have different signs. If one is positive, other is negative. Okay, so it means f of a and f of b, if both have the different signs, then their product is what? Negative or positive? This is negative. Okay, so this is the condition that we imposed, that the function uh, heights must be different in sign at the endpoints. So if this condition holds, then let me write a conclusion, and we just seeing that conclusion in the graph over here. Then there exists a point P, where this point exists between A and B, okay, such that f of P is what? It is 0. In other words, try to understand in another way. If function is continuous and one height is positive, other height is negative, function will travel from positive height to the negative height, and it will cross x-axis. It is going to cross the x-axis. Whenever it's is crossing the x-axis, that is the point where the function is becoming 0. The value of the function is becoming 0. So we are interested in what? We are interested to find that point where the function is becoming 0, where f is becoming 0, because that is what? If I write an equation x minus cos x equals to 0, so this is my equation, this is my problem, and what I wanted is, I wanted a solution of this problem. What is the solution of this problem? A point, a real number at which the left hand side becomes 0. I wish to find that point. Okay, so what this theorem is giving us the information that if you can find a certain interval where these two condition holds, then then we are sure that the solution lies in between that interval. So if I try to summarize in a one sentence, so this theorem ensures us that this is the region where you can find your solution. It identifies you the region of interest. Okay, it identifies that region. Okay, because whenever you will dealing with this equation, first you will not know, maybe the solution lies in this interval or maybe the solution doesn't lie. We have to make sure ourselves that the solution lies in that interval. For that, we can just need to check what? Let's put a question. Show that x minus cos x equals to 0 has a solution in interval 0 to 1. Okay, so there is a question which show that the solution lies. It doesn't ask find a solution, it just says that show that the solution lies over there. Okay, so how to show that? We just need to see these two conditions. Okay, let's try the first one. Okay, f, what is f? F is x minus cos x. This is f. Okay, so x is a first degree polynomial which is continuous everywhere. Cos x is a trigonometric function which is continuous everywhere. There is no divide by 0 issue, there is no such problem. Okay, so both functions are continuous everywhere, and sum of the continuous function is a continuous function. Okay, so x minus cos x is continuous on this interval. It is continuous everywhere, so it will be continuous on 0 to 1, no problem. Second thing, we need to check what are the function values at the endpoints. Okay, so let's call it as f, x minus cos x. So if I calculate f of 0, what is this? 0 minus cos 0, which is minus 1, and it is negative. And f of 1, which is 1 minus cos 1, just an advice, okay, and you need to be caution in this course. Your mode of calculator must be in radians, because radians are numbers. Okay, so they are the numbers. So your mode of the calculator must be in radians. Okay, So you will be requiring the calculator all the times. Okay, so the value is coming as 0.4597 up to 4 decimal places, so that is a positive value. In other words, at one height the function is negative, another function is positive. So what is the product? Is it positive or negative? It is negative. So if the function is continuous on some interval and the function value at the endpoints have the alternating signs, okay, then there is a point. So what is the conclusion? The conclusion is there exists a point in this interval where, let me write an open interval because both 0 and 1 is not 0. So there exists a point in this interval where x minus cos x will be 0. Okay, or you can write p minus cos p is equal to 0. Okay, just to have a more let me just write f of p, sorry, p minus cos p is equal to 0. In other words, we identify a region in the real number system, in the whole real line. Okay, this is the region of interest. Here the solution lies. Okay, and we are sure that the solution lies. Okay, so this corollary of the intermediate value theorem, which you have learned in your calculus course, help us in identifying a region of the solution of a one variable equation. Okay, it identifies that this is the region where you need to look for. So if there is a question coming up that you need to just show that the solution lies, so you just need to see these two conditions. If these two condition holds, then you can write the conclusion. Okay, so now let's try to explore this a bit more. Okay, if one height is positive, other is negative, okay, so the function will be crossing x-axis. So when it is crossing x-axis, this is the point where, this is the point P where f of p is 0. So if there is a product of function value at the endpoints as negative, then function have a point in between a and b where it will be becoming 0. You can understand in this way, if it is a continuous function and one of the height is negative, other is positive, so function has to travel from negative height to the positive height, and once it's traveling, it has to cross the x-axis. That is the point where we got a solution. Okay, so now let's try to explore a bit more in terms of the example we just started. Okay, so I'll try to make more scenarios. Okay, and we try to improvise this statement. Okay, the continuity of the function is over there. We are not making any changes with that, but we'll be more exploring this condition. Before I go in detail to the condition f of a, f of b less than 0, we just seen a case where one of the height is positive, other is negative. If, for example, such is the case, then you can just draw the same analogy. Okay, if one of the height is negative, other is positive, actually the product is negative. Okay, so you can just draw the analogy from the previous case that we got a solution. Okay, so we will have a solution. Now, rather than this, I will continue with the first graph, and I try to develop more scenarios. Okay, so this is a point A, this is a point B, this is the height, this is the point A, and this is the point B, and this is the height. So these are the heights at the endpoints, and the function is continuous. Let's start with this. Okay, that is the first case that we started with. Actually, we just, for example, if this is the case, how many solutions we have? There is only one solution. How many times it crossing the x-axis? Only once. Okay. Now, because it has to come to this height, there can be more options. For example, if I say there are more than one solutions, okay, there are more than one solutions, then we need to see how many more. Okay, so for example, if I start from here, if it has more than one, so let me just cross one time. So this is one. If it is more than one, then I have to cross the x-axis. So once I'm crossing the x-axis, okay, I've crossed the x-axis, we got a second solution, but the terminal point is over where? It is over here. So I need to come back, okay, because it is a continuous function. I can't take jumps, okay. So I have to come over here. So how many solutions now we have? 3. So it means if this condition holds, then if we have more than one solution, that cannot be 2. That cannot be 2. Okay, that can at least be then 3. Okay, now let's go beyond 3. If for example we have more than 3 solutions, so if I start from here, let me just count the 3 solutions. So 1, 2, and 3. Now if this number of solutions are more than 3, then I have to again cross the x-axis, and if I have to cross the x-axis, I have to come back at this height. So how many solutions I have? 5 solutions. So let me just write over here, if f is a continuous function on this interval and if this condition holds, then there exists at least one point. At least one point. Okay, the minimum requirement is there is at least one solution. Okay, so, and we can also add over here, if number, if there are multiple solutions, then then the number of solutions are odd. There are odd number of solutions. If there is more than one solution, then there are 3 solutions or 5 solutions, and you can continue with that. 7 solutions, 9 solutions. Okay, so if there is not one solution, more than one solution, this condition holds, then we have either odd number of solutions. Okay. Okay. If you have any question, you can ask. Okay, there is one question I need to ask. For example, I give you a scenario. This is a point A, this is the point B, this is the height f of A, this is the height f of B, okay, and I have more than one solutions. Okay, so please follow this curve I'm going to draw. If for example it crosses x-axis, I got one solution, I have more than one solution, let's say. So if I draw like this, okay, it's just, it has not crossed the x-axis, okay, it just hit the x-axis and come back. Okay, so how many solutions we have now? This is P1. Here we have, actually we have 3 solutions. 2 solutions are same. Okay, 2 solutions are same. Let me tell you how. If for example I ask you to write a polynomial which has 1 as a root, a real number 1 as a root, okay, so what you will write? For example this. So this is a polynomial which has a root 1. And if I ask you, okay, write a second degree polynomial which have a root 1 and it has a multiplicity 2, okay, write a polynomial in which 1 is a root and it has multiplicity 2. It means 1 is a repeated root. How many times? Multiplicity times, 2 times. So it means I have to write x minus 1, x minus 1. So this is x minus 1 whole square. Now you see the geometry has been changed. The how many multiplicity, the word of the multiplicity will change the geometry. Okay, so here the solutions are 3, okay, because it's a tip of the parabola. So we got 2 solutions, okay. So we got 2 solutions over here. It's like an x square. If you plot an x square, and if you say what is x square equals to 0, x equals to 0 at what? At 0, na? So how many solutions we have? We have 2 solutions, 0 and 0. Okay, 0 and 0. So we say it like this: 0 is a root with a multiplicity 2. Okay, so that's why whenever you just kisses the x-axis, you got 2 roots. Okay, you just crosses you just hit this point, then you got 2 roots. Okay, so we have 2 roots. So so the total number of roots are 3, but 2 are same. Okay, so be aware of such questions. Okay, in somewhere you got. Okay, so they make you confused. Okay, so you have to have an idea of multiplicity. Now I just wanted to explore this condition more in a different way, and that is, so let me just so we have a question that how we are sure that the curve we just have got 2 roots. Why it can't have 3 roots? Okay, why it can't? Because it's a parabola. That's why I just plotted x square. If you see, and for example x cube, okay, x cube, so it will have an asymptote. So it will not just take a turn back, it will go down. Okay, so if it is the this will be a parabolic shape. Okay, and obviously if this parabola is becoming like this, then we might have more roots. Okay, for example x power 4 or x power 6 or x power 8. Okay, so then this will be becoming closer. Okay, okay, so let me now just go with another condition, which is continuity is over there, but let's explore what happens when f of a, f of b is greater than 0. For example, can we have a possibility that if f of a, f of b is greater than 0, can we have a solutions? Okay, so we just need to see that for this, hopefully you'll agree that if the product of the two values is positive, then either both are negative or both are positive. Okay, so both needs to be positive or both needs to be negative. Okay, so let me just take a view of a point A and point B, and this is one of, if for example both are positive, this is f of A and this is f of B, for example. Okay, and let me also draw some more options because we will be concluding a thing. So this is the height. Okay, let's try to see if f of a, f of b is positive. It means both are positive, let's say. Okay, you can draw the same procedure I'm going to do with both are negative. Okay, so let's say both are positive. It means both heights are above the x-axis. Okay, so one of a scenario can be like this. How many solutions we have? So we got no solutions. Okay, so we got no solutions. Okay, another scenario can be like this. Okay, so how many solutions we have? So we got two solutions. For example, we got more than two solutions. For example, we have more than two solutions. So let me just take two. So if this is the scenario, we got more than two solutions, then we need to come down. Okay, we need to cross axis. Once we cross the x-axis, the term ultimately I need to go at this height. So I'll go back to this point. Okay, so how many solutions we have? Four solutions. So if I keep continuing this observation, for example, we have more than four solutions, then the solutions will be six. So it means, coupled with the continuity, if we have that condition, then let me write the conclusion with the condition that f of a, f of b is greater than 0, then there is a possibility that we do not have any solution. Okay, this is about the first observation. There is a possibility. Okay, and if there are solutions, then they are even in numbers, in count. If you count them, they will be even. Okay, even number of solutions: two solutions, four solutions, six solutions, eight solutions. Okay, so now if I just pose you a question, so we have this scenario where f of a, f of b is less than 0. Okay, and we have another scenario which where f of a, f of b is greater than 0. Okay, so which is the wise way to go with? A one with at least one solution, or one with the possibility that we may not have any solution? We have at least one solution. Okay, so that's why we go with this possibility as we proceed in the finding the solution. Okay, so this is a critical condition. Okay, and if it comes into your mind a question that if it becomes 0, let's say f of a or f of b is equals to 0, then one of them must be 0. Either f of a is 0 or f of b is 0, or both are 0. If f of a is 0, then a is a solution. We got a solution. We don't need to search for it. Okay, so that's why we can only argue that either it is greater than 0 or it can be less than 0, because at equals to 0 we got a solution. Okay, so with this actually information, which is just to conclude about the corollary of the intermediate value theorem. You just need to check if the function is continuous on the given interval, and if we have the alternate signs of the function at the endpoints. If that condition holds, you are sure that the solution is going to lie in that interval. Now this is about the identification of the solution in a certain interval. We can identify it. Okay, now how to find a solution, how to find the one, that is now a next question, that how to proceed towards a solution. Okay, we'll just in this lecture be trying to develop a basic technique, a very basic technique that takes us towards the solution. That technique is called the bisection method. It is also called the method of root bracketing. Okay, so let me just take an example and we try to apply a procedure that how we can go towards a solution. Okay, so let me write over here. Okay, let me write over here approximate solution of x equals to 0 on this interval up to okay. So this is the question. Let's first try to understand the question, and then we'll proceed towards a procedure uh, in general terms. So this is a question, and we need to try to find a solution of this equation in this interval. So first we need to make sure, do we have a solution in this interval or not? We just check in the previous uh, just working that x minus cos x has a solution in interval 0 to 1. Okay, it has a solution because it is a continuous on this interval and the function value at 0 and 1 is negative. Okay, so we are sure that the solution lies in this interval. There is a word up to 10 raised power minus 3. Now this is a key point that you need to connect, that we want to have a solution up to this accuracy, because if I wanted to have an approximate value of a pi, that can be 22 by 7 up to 2 decimal places or up to 3 decimal places, but not beyond that. Okay, so when you say up to certain decimal places, it means you want a solution up to that point. We don't need a 0 that is 0 exactly. It can be 0.0001 and it will be sufficient for me. Okay, the solution will be sufficient for me. Okay, so that will be a thing and we will be using it. Okay, let me just write over here, draw a line, and we will be using this line. Sorry, it's not state, but it should be state. So 0. So I'm just plotting an interval which is a equals to 0 and b is equals to 1. Let's also try to go with the generic form, which is, for example, f of x is equals to 0 on an interval a to b. Let's say any general problem and on a general interval. Okay, on any interval, and we know that the solution lie in this interval, and up to 10 raised power minus n, it is a general accuracy that we wish to achieve. Okay, so uh, the first intuition is that uh, since we need to go towards a solution and it lies between the interval a and b, so might be it is the midpoint of the interval. Okay, because midpoint is a point which is connected with both the points. Okay, so the bisection method says find let's try to find the midpoint of a and b. Okay, in this case a is equals to 0 and b is equals to 1, so I'm just calling it as p1, and it is equals to 0 plus 1 divided by 2, so it is 0.5. And we need to check, is this a solution or not, because the solution lies between 0 and 1 and we got another point which is a midpoint. We wanted to see, is it a solution or not. Okay, so how can we check it? We need to plug this value into our problem. Okay, and let's plug this value into problem, maybe it gives an answer 0. Okay, so I'll check, this is p1 minus cos p1, or in other words 0.5 minus cos 0.5. Okay, so if I check this value, please put your calculator mode in radians. Okay, so we have minus 0.3776 approximate. Okay, so we have this value. Now is it 0 up to the number which is over there? What this number is? This number is 0.001123. Am I right? So if I use this value p1 and I plug into the function, is this number is close to this number or not? Now that is very much away from this number. Okay, so I'll say I did not get an accuracy that I wanted to achieve. Okay, so if this is a midpoint, which is p, and we have a 0.5 value, and it is not a required solution, then I need to further go towards finding a solution. To go further towards finding a solution, I need to see what is the sign of function at p1. Okay, let me write a sign of f because that is very important. Let's see what is the function sign at 0. Hopefully you remember f of 0 was 0 minus cos 0, so it is minus 1. It was negative. The sign is negative. The sign is negative. And what was the sign at 0.1? It was a positive, 0.4 value something. Okay, so it was positive. Let me just draw it. So the sign was positive. Okay, okay, if this is not a solution, what is the sign at this point? It is negative. If it is negative, now you got two options, two subintervals. This is a subinterval 1, this is a subinterval 2. By identifying a sign, can you tell where the solution lies, in I1 or I2? We are sure that the solution lies where the function have the different signs at the endpoints. So if this is an interval, the signs are same. And if this is the interval, the signs are different. If the signs are different, it means I need to find a solution in this interval. My solution lies over here. Okay, so it means I need to discard this portion. Okay, I don't need it. Okay, so in other words, I need to look in this particular subinterval. So I make this point A travel from here to here. Okay, because I don't need A now at this portion. So let me just write over here, this is A, which have now a value 0.5, and B has a value 1. Okay, at A we have a sign negative, at B we have a sign positive. Okay, so now let's see what is the midpoint of this interval. So midpoint of this interval is A plus B divided by 2, which is 0.75, because 0.5 plus 1 divided by 2 is 0.75. So it is 0.75. Okay, I just at times write to just to make sure that how many midpoints we're going to calculate. Okay, just to make sure. So this is my P2. Now I need to check, is it a solution or not? How can I check that? I need to plug this into the function. So this is 0.75 minus cos 0.75, and the value will come out as 0.0183. Okay, is this value is near a point 10 raised power minus 3, because this much of a accuracy I wanted? It is not. Okay, so I need to keep finding a solution. Okay, so if I need to go finding a solution, I need to check what is the sign at P2 of the function. What was the sign? It was positive. Now we have a left subinterval and a right subinterval where the solution lies. in the left one. Okay, so it means I don't need this portion right now. So which variable is going to travel? B will travel from this position to this position. Okay, so now B is 0.75. At B we have a sign positive, at A we have a sign negative. Okay, so we got this portion. Now we'll do what? We'll again do the half. So the half is 0.625. Okay, so you have to do the half. So it is P3, which is 0.625. Again, you need to do what? You need to check, is it a solution? How you check it? You plug into the function and see what is the value. Is it 0 up to the accuracy I wanted or not? Okay, so the value is minus, am I right? 186. So this is the value I have. Okay, so at P3 it is not close to the accuracy I wanted. Then I need to check the sign of the function. What is it? A negative. Now we have a solution in left or a right subinterval. In a right subinterval, the signs are giving you away. Okay, they are leading you towards a solution. So now this is value of A, which is 0.625, and B 0.75. Now you can see in a slide that the procedure is easy. You just need to identify an interval or a subinterval where the solution lies, and you need to do the half. When you find a midpoint, you need to check at the midpoint, is it a solution? If it is not a solution, you need to see the sign of the function at that p-value. So that will decide in which subinterval you are going. Now, if you just take an example like this, if for example I ask you to just take a one step, okay, if I take a one step, okay, and if I ask you, the next step will be the half of the previous step. So you'll take the half of the previous step, and then half, and then half. Then after some time you will see that I will not be moving, because I will be that much close, my actually feet are that much close. The length of the the step I'm taking is becoming smaller and smaller. What is happening? The thing that is happening is that anyone, what are these? These are the midpoints that I'm generating, okay, with a certain observation. These midpoints will generate a sequence. So if you just collect them in this way, you have a sequence. Okay, that sequence is called a sequence of midpoints, and it is taking you where? It is taking you towards a point P. When you plug into the function, you'll get a 0. Okay, and if that P is an irrational number, you will not be able to find it exactly, but you will be able to find exactly to the machine you are using, maybe to the 15 decimals or maybe to the 10 decimals. Okay, you will find that. Okay, so it means if we talk about in mathematics way, you will have an infinite sequence, but if you talk about on a computer system, you will have a finite many terms that will uh, that you need to compute to get a certain accuracy. Okay, so I'll just conclude this, because I will be you'll just have an idea. So this is actually a sequence Pn, okay, which is going towards what? A point P, and this point P has a property that this function will be 0 at that point. But your accuracy, your tolerance will decide that how many steps you need to do. When I use the word steps, it means the value of n. P1, P2, P3, P4, P5, P6, how many solutions? If you see this slide, okay, you will see that we got the solution up to 10 raised power minus 3 at the P10. So I need to do the 10th iteration. So the word is iterations. So this is the word iteration comes. One set of statements that we need to generate is called a one iteration. So we need to do 10 iterations of this method to reach an accuracy of 10 s power minus 3. Okay, so we'll see in the coming up lectures more about the algorithm development of this method, and we'll see some more examples coming up. But to conclude, in this particular lecture, what we did was we just continue with the prerequisite knowledge that we required from the calculus, that is the intermediate value theorem. And we're very fortunate that the intermediate value theorem is directly connected with the solution of the one variable equation. They are helping us in identifying a region where the solution is lying. Okay, and then we talk about that whenever the condition, which is f of a f of b is less than 0, or f of a f of b is greater than 0, which condition is a more wise condition to go with. Okay, and lastly, we in the trying to find a solution to, once we identify that, we have done certain steps, which is actually called the method of root bracketing. It's also called the bisection method. We'll continue this working, and we will develop the algorithm in the next lecture. Okay, thank you so much.